Okay, well, I have a fair amount of material to go through. I hope I get through most of it. Here we go. So, if you guys ready? Okay. So my name is Skip Hovsmith. I work for Critical Blue, and we are a mobile API protection company. We've been around for over 10 years. We do a lot of kind of low-level, close to the hardware, software optimization, and we've taken some of that expertise and applied it to mobile API security. I actually started off as a chip designer, and I've been trying like heck to work my way out of chip design. Did a lot of work with custom accelerators, trade-offs between hardware and software, custom acceleration software design. Drove us, Critical Blue, into embedded and Android optimization on some exotic platforms. One of the last projects I did was on an HSM to accelerate crypto, so that kind of got us into the mobile world and the security space, so we put them together to launch actually our first product. My role at Critical Blue is growth hacker for Approve, which is an awesome job to have because it basically means I can do whatever I want to help grow the product. So I can go out and talk to people like you guys. I can write blogs. I can actually hack code, make features happen on the product. So it's a really cool job. I do blog on Medium, also on Critical Blue's Approved blog site. Feel free to go check out our website at approved.io. What I'm going to talk to you about today is a hypothetical company called ShipFast. They operate a delivery service where a bunch of shippers can just pop online with an app and just crowdsource deliveries in kind of an Uber-like fashion. It's hypothetical. It's all open source code we use for demonstration purposes, and it's all available on GitHub. There is an evil add-on that gives shippers an edge called the ShipRaider web application, which I'll be using, and it basically will be a back and forth about how the API will evolve to as ShipFast tries to prevent ShipRaider from doing certain things. At this point, I would usually regale you with a story about how fast APIs are growing. I'm sure you all know that. What I really want to focus on is how the apps are evolving and how that combined with APIs is really shifting the way data is flowing. So used to be you'd get a very simple web application. There would be a simple browser client. It would be really mostly just about presenting information, presenting a web screen. As you move into native mobile apps and say single page web apps, more and more the business logic migrates onto the browser platform or the device platform if it's a mobile API. And now the applications themselves are demanding a lot more data. They're a lot more open-ended, a lot more interactive. So there's a lot of data passing back and forth across these APIs. So securing your APIs is pretty important. APIs make reverse engineering things, as easy as can be. If it's a public API, it's probably pretty well documented. So you can just go and see exactly how APIs are being called. If it's not public, but it's in a structured style like REST, if you can find a hook into, say, a get operation, you can tamper with a verb and try a delete operation and see if that works. So getting at these APIs, if you're an attacker, is pretty easy. Oftentimes, the implementations leave a little bit to be desired. Leaky APIs will disclose information, of course, on what they return, but also if you can force errors, you get a lot of information about that as well. And there's a lot of promotion saying you need to document your APIs, a lot of easy auto-doc tools, so you can accidentally publish your API if you're not careful. And if you look at the very bottom, here you see we've actually published an admin/shutdown API call that maybe we didn't mean to publish out for the world to see. Usually we talk about these things in kind of a client-server mentality. We say, well, I've got an app. It makes an API call to its travel app API, which is its server. Reality is nothing like that. If you're at all successful, you've got multiple platforms, native apps, hybrid apps. You've got lots of legacy code. They all have different versions. You've got web apps running. They're running not to one API, but to multiple backend services typically. Each one of those has versions. They're done by different people. So if you're an attacker, there's a lot of complexity here, and you want to exploit it. So here's what ShipFast looks like. We're going to focus on the shippers app here. Someone who wants to ship a package would go to the website or to the customer app and would just go ahead and post up a package that they want to have picked up and delivered somewhere. We're just going to be showing a Android mobile app throughout this. So the first thing that the shipper would do to find out if there are packages available that he can serve would be just to log in with a standard kind of OAuth type login, and I'll talk more about OAuth later. We're just using auth0 here as an example login. Once he's logged in, he gets to a screen where he needs to indicate that he's available to find out where the nearest shipment is. And as you see up here, he'll get information about the shipment. It'll show up on the map. And what's going to be important here is that there is a gratuity that is included. The driver will be paid for the delivery, plus he's going to pocket the entire gratuity. So in theory, he would love to find the big gratuity type deliveries. Of course, ShipFast is really not interested in giving him all the gratuities. What they're interested in is maximizing their throughput. So they want to give him the closest package to pick up and go deliver. So when he's ready, he would click I'm available down in the bottom right here. And what he gets is the closest delivery point. Unfortunately, that has $0 of gratuity. But that's what he's given. So if he's using this app, that's what he's going to do, and he's going to get paid for the delivery. When he arrives there, he will, when he's ready to go, he will accept the delivery. He'll drive to the collection point and indicate that he has collected it. He will then drive, probably not in this straight line, to the endpoint, and when he's done dropping it off, he'll mark it as delivered. And then he'll see a log of all the deliveries he's done for the day and all those big gratuities that he's made, which is so far 0. This is what a sequence of API calls would look like. The first thing he's going to do is log in and get a user token. The app will check and see if he is actively delivering something, because it's not going to give him another package until he's delivered the first one. And then comes an important call here, which is the app is asking, where is the nearest shipment here? And so that's going to be an important thing to possibly abuse to see what other deliveries we can find around. He'll accept the shipment, go pick it up, deliver it, and hopefully collect a gratuity. So a very techie guy came along and said, hey, I can help out the shippers and give them a little edge here. So he created a web application called ShipRater. And what it is attempting to do is to find where the biggest gratuities are. And for now, it's a web app. It could be a standalone application. So the first thing that ShipRater is going to do is the user is going to go ahead and log in with his usual ShipFast login to identify himself to the ShipFast platform. And this is not an attack per se. The shipper is interested in getting the biggest gratuity, and he freely gives this information away. So there's nothing bad going on at this point in terms of the logon, except for maybe that ShipRater is looking like ShipFast through the login process. So once he's logged in, he's given a screen, and you can see the OAuth token value there, just because this is a very techy implementation. And you can see the setup here to basically make that get nearest shipment call at various longitudes and latitudes in basically a circular sweep that gets set up. So I can find all the packages within a certain area. So I go ahead and indicate that information, click it through, and I get a list of possible packages, and I immediately zoom in on the big gratuity one, which isn't too far away, and I go and try and grab it. So at this point, it actually marks that I have accepted this for delivery. I then move over to my ShipFast application, and I log in. It checks to see, am I delivering something? In this case, it now says, yes, you are delivering something, shows me the map. I go ahead and make the delivery as usual and mark it done. So what we're exploiting here is this get nearest shipment API call. We're just using it repeatedly in a way that really wasn't intended. One thing I neglected to mention is that once you log in, the bearer access token for the user will be supplied with every API call, and the API key, which really indicates that it's coming from the ShipFast app, is going to go through with every API call as well. So the user authorization was freely given, so that's not the problem. It really appears that the API key must have been leaked somehow, and so the ShipRater application is using that. So the first thing we want to take a look at is that key, does it appear to be secure in motion when it's going across the communication lines? Typically, you would insist on using TLS or HTTPS. Here, TLS is a handshake protocol that establishes encryption between the client and the server, and it works great as long as you can trust that the certificates that are being handshook and passed back and forth are legitimate. There is typically one way where the client trusts the server. There's also two-way mutual TLS authentication where the server also is authenticated back against the client. So what you're trying to prevent, and what you may not be successful in, is a man-in-the-middle attack. So an attacker will try and get in the middle of this encrypted communication. Because we're using a mobile app, the attacker is free to go and get the mobile app, download it, set it up, and what he will try and do is create a fake certificate that indicates that the server for that certificate is the server that he's trying to get in the middle of, and he installs that fake certificate on the mobile app and says, "Trust me, this certificate is good." So at this point, he's set up a man-in-the-middle attack where to the app, he looks like the server, and to the server, he will go ahead and look like the app. He can snoop on this traffic. He can modify this traffic. So this is one way he could potentially get a look at what that key is, because it's being sent, although encrypted. If he can break the encryption, it's sent in the clear. So typically on a mobile application, what you will do is do something called certificate pinning. And basically on the client, you would put a white list of accepted trusted certificates. So if somebody tries to come in with a phony certificate, it would not be a certificate that you would value. In theory, you would say you don't trust it. So the attacker is kind of stymied at this point, and that they can't break this whitelist per se. Though I will note that the whitelist is itself another secret that might be snoopable and found out if you look in the app itself. So pinning is a pretty good solution for mobile, but it's not as widely adopted as it could be. As I said, the keys themselves in the whitelist are additional secrets. The question is, what happens if a certificate expires, or if you want to rotate a set of keys? It becomes kind of a maintenance and upkeep issue. How do I get fresh keys onto the device without causing my entire user base to have to sort of upload and update applications, which is something that's notoriously hard to do. So people get a little gun shy about that. And even if they do it, there are frameworks available for mobile devices that can hook different calls and try and spoof them. So in this case, there is on Android something called SSL Trust Killer, and if you're not looking to prevent that, it can go ahead and when the request is made saying, "Is this on the whitelist?" it can go ahead and return, "Yes, of course it is," and you can get right past this pinning if you want. So in our case, ShipRaider was not going across TLS, was not trying to break the pinning. So far so good. The next question is there something leaking off the device? So is this secret, the API key, is it secure at rest? Well, Ryan Hellier is one example of somebody who made it pretty easy to find keys. He actually wanted to put his brand new shiny open source project up on GitHub. He was running on Amazon, and he very carefully ensured that there were no keys present, and he went ahead and published this to GitHub. Unfortunately, there was a backup file that had the keys on that. So within hours, he had a $6,000 bill from Amazon where people had found the access keys to Amazon and used it. So unfortunately, one of the most easy ways to leak a key is to simply publish it up to GitHub by mistake. We didn't do that, fortunately, but we did something almost as bad. When ShipRaider took a look at the application, he started with the APK, which is the Android package that is downloaded from the Play Store, and he just unzipped it. Took a look at the manifest file, which kind of keeps everything organized, and right smack dab in the middle of that manifest with no encryption whatsoever was the API key. So that was pretty much a no-brainer to find that API key. Once you found the API key, he was off and running, just plugged that into his application, and he was free to call the API as he wanted. So API keys need to be held on to pretty closely if you're trying to prevent that from happening. What might you do if you did get breached? Is there something you can do to mitigate that? Well, the question comes down to, can you figure out this traffic does not look good? Is it abnormal in its frequency or in the patterns that are being called? So is it good traffic or bad traffic? The classic approach to this is a rate limiting kind of approach. Basically, you're looking to see, is this API being called too fast, too frequently? Is there a quota? Oftentimes when you sign up for a free service, it's free for the first 1,000 calls every day, something like that. So that's all being done through rate limiting. You can also look in very short bursty traffic. If you see big bursts of traffic, you might want to shed that too. So in ShipFast's case, if you do a radius search, you're firing off a bunch of the same API calls with different latitudes and longitudes. So that might trip up a rate limiter. These can get pretty sophisticated, so for certain expensive calls, which a DDoSer might be using to try and, say, force your database to do more work, you might have tighter limits on that than some of the other calls. It's all kind of a game, and it really boils down to a game because if you are supplying an application, the last thing you want to do is lock out legitimate traffic. So a lot of the users are very conservative in what they rate limit. So it sounds good, but it isn't necessarily that effective when people are quite conservative. Another approach you'll hear about is behavioral API security, where we're actually trying to do pattern detection. In ShipFast's case, you could view this as if you see a user suddenly popping up at different places around the map. If you measure the time difference, he's traveling faster than somebody could travel in a car. So you could say that as a behavioral form of detection that you're doing. Typically, behavioral API approaches employ big data with machine learning kind of techniques that adapt to the traffic and learn from the traffic over time. The biggest challenge here, kind of similar to rate limiting, is that you tend to be lenient because there tend to be false positives. So the last thing you want to do is lock out a customer who's legitimate. Their traffic looks a little strange, but it really is legitimate traffic. You don't succeed if you do that. So again, you tend to have loose constraints in that case. So ShipFast is a little pissed off that their traffic is going and grabbing the big gratuity pieces, and they want to strike back. So they think about the problem, and the first thing they do is they add request signing to their API calls. So we already have an API key, and we're passing that across the API call. Now we're going to add an HMAC type signature to this. What we do is we add a secret paired with the API key, and we're going to use that to sign a combination of the request plus some semi-randomized piece of information. In this case, the easiest one to use is the OAuth token. It changes periodically as it times out and you get fresh tokens. So that gives a little bit of entropy in the solution. We go ahead and take that and sign it with the HMAC secret, pass it across. The HMAC secret is known on the server, so it goes ahead and repeats that calculation using the pieces of entropy and the API call. And the secret, it's able to confirm, yes, the signature does appear valid. So the good news is that it proves that the request is untampered when it came through. The secret itself is never transmitted. It's still just sitting there on the client and on the server. The API key still goes across, but without the secret and the knowledge that we're doing an HMAC signing, that's okay. And I guess I should point out also that in addition to signing, if you want to, you could fully encrypt this communication. So if you were running TLS, you would have sort of two layers of communication here. The first encryption at the TLS layer, and at the application layer, you could have a second layer of encryption. It slows down your process a little more to do the decryption, but it adds a little bit more security through, so it's your choice. So you've got a secret now sitting there, and you want to make sure that it's as hard to find as possible. The bad news, no matter what you do, if somebody wants to find it, they will eventually figure out how to find it. The initial thing you do is you want to obfuscate your code, the native code running on your mobile app, and both Android and iOS come with sort of basic free obfuscation. So they'll change variable names, and they'll potentially vary the control flow, make it harder to understand what the code is doing. So that gets you down part of the way, and you can buy more professional and higher level obfuscation, which will do more and more obfuscation of the code. You can roll your own. which is what many people will try and do. They'll try and build up some sort of custom secret. If you've got a secret just sitting there statically, it's something you can go look for by itself. So a common approach will be to break that secret into a bunch of different pieces, stick them in different places in your code, and through some tricky and quite often some sort of XOR-ish-like function, go ahead and reassemble that code to create the secret. This has to be done at runtime, which is good because the secret doesn't exist in one place, but it has to be very deterministic because the secret you end up with, it has to be something that the server can also recreate. So you don't have a lot of entropy in this case. It's all in how well you can hide those pieces. You can take this to extreme with white box cryptography, where you take a secret and you actually dissolve it thoroughly into your code, and rather than storing the information, you will convert it into some sort of algorithm to even further hide what's going on. So that's good if you have a secret to bake into your code. It's bad if that secret is uncovered, you have another maintenance problem where you have to download a new white box download a new white box or go through some sort of updating process to go through the secret. Additionally, there are software and hardware backed key stores. So you put a secret in there. The secret doesn't come out, but you can use the store to do certain operations for you, like an HMAC operation, for example. If a device can be rooted, the software backed ones are pretty vulnerable, and the hardware ones using something like ARM their trust zone technology is kind of hard to use, so it hasn't been used too much in the industry, but it's another approach you can go for. So what ShipFast decided to do was to go ahead and calculate the secret at runtime. So they avoided just storing this one big fat secret to go after, and they went through an XOR type calculation to split the piece in and XOR a bunch of things back together. And it is deterministic, fairly easy to compute. So they started with a static secret. They actually calculated this obfuscated secret from that seed, and that's what's used in the HMAC. So how did ShipRaider respond? Really quickly, unfortunately. They broke the HMAC pretty darn fast. Sometime later, they were back online, and examination of their code said, yep, they got it. The question is, how did they get it? Well, in the Android world and in iOS, there are a lot of good reverse engineering tools available, many of them free. So it's very easy to decompile the code and to go ahead and repackage apps, run debugging on apps that were maybe not intended to be debugged, and we can use these frameworks to monitor and or change the runtime behavior. So what they did in this case was they repackaged the app so that they could debug it, and in concert with the ShipFast client itself, they set a breakpoint in the ShipPoint client that they're trying to debug just before the first HMAC type operation is sent. And as you can see, it hit a breakpoint, and after a little bit of cycling, they came right up to the secret that's being used. So they avoided that complex, messy calculation altogether. They just found it right before it was ready to be sent. It's a deterministic secret, so they're good to go. So they now still have a secret. Didn't have to change ShipRaider very much, just had to change the secret. So I'm going to fly through user authorization. OAuth 2 and OpenID Connect is what's used in our application. It's becoming pretty standard as we go through. So OAuth 2 is a stress and authorization protocol. It gives the resource owner the ability to specify scopes that a client is allowed to access on the resource server. So it's not actually the authentication of the user, though it uses the user's credentials to have someone else authenticate that that user is who they say they are. So it uses that on the side. It's often extended with OpenID Connect to do things like introspection, discovery, and revocation of tokens. There's a lot more standardization in that flow, so it's almost becoming interchangeable, OAuth 2 and OIDC. There are different grant types depending on whether there's a human in the loop or not, whether you're doing something real legacy or something more modern. For a user in the loop, the authorization code grant flow is by far the most popular. This is what the abstract protocol flow looks like for no matter what flow it is. The first thing that a client does is make an authorization request. It's asking the resource owner, which is usually the user, but could be somebody who's delegating something to a client. It's asking the resource owner to say, yes, I grant this client the ability to access this information on the resource server. At that point, the user is asked to present their credentials. It goes through to an authorization server, which verifies the user is who they say they are, and then go ahead eventually and issue some sort of access token. And then that access token is presented to the resource server, who checks it. If it's signed correctly, it hasn't expired, then it goes ahead and returns the protected resource. So it completes a successful API call. This is what the code grant flow looks like. And the important takeaways here is there's an authorization step and there's a backend step. In the first step, the first thing that the client, in our case the ship fast application, would do is delegate the authorization step to a user agent, which is also kind of known as the front end in OAuth process. And the user agent is typically the browser that's sitting on a device. So it redirects onto the browser, and the user sees a authorization screen. You've probably seen them before on Google or whatever you want to use. You say, yes, that I want to authorize this access to my backend information. You give away your house and your kids and everything else, and it lets you go ahead on. So at that point, it goes over to the authorization server, verifies that everything looks good, and after checking out their credentials, it will return an authorization code. That code then redirects back to your application, and then your application goes through the back end of this flow back to the authorization server, and the code is exchanged for an initial access token plus a refresh token. Why is this split into two pieces like this? Why don't we just return the access token straight off? It's basically to separate the front and the back end to make sure that the access token is never seen by the user agent. And the user agent is not involved in any of your application's business. So the credentials are on the user agent, and the access token is in the back, and so there's no leakage of information, hopefully, between those two pieces. An access token is typically a JOT, a JWT token, with a limited amount of lifetime that is chosen by the user. It might typically be, it depends, a banking application might be a few minutes. A game, if you have to log in, might be for 6 months. It's up to the user's choice. But we'd recommend keeping the access token lifetime short. And when you go ahead and make an API call with an access token and it fails, it comes back and says it's invalid, then you go ahead and then take your refresh token and send that back to the authorization server. It checks out your environment and sends you back a fresh access token and typically a fresh refresh token as well. So both the access token and the refresh token and best practices will be single-use kind of tokens. There are a number of ways that you can attack OAuth. Most of them have been plugged up because it is quite popularly used. I just picked out one here for mobile devices because it involves a leaky secret. It's called PKCE, PKCE. And in this case, what we want to do is enable the to ascertain that the front end piece, when it goes through, has to be the same set of operations as the back end piece. So looking at this as it goes through, we start on the front end asking for some information, and we issue a code challenge value with this. That value is sent over to the authorization server where it's stored. This is just a hash of a random value, and the hash is known to your application. So when you come back around to the back end sends the original code verifier, which is the unhashed value, and the authorization server takes that code verifier, hashes it, and compares it to the code challenge, which was the hash that it got originally from the front end. And if they match, then it will go ahead and give you back your access token and your refresh token as you go through. This is typically used on native devices where they just know that client secret is not really going to be worth too much. It's easy potentially to steal. It's a static secret. So in some cases, like in Google OAuth implementations, for example, there is no client secret even used. They're relying on this PKCE mechanism to link the front and the back end's integrity. So these secrets seem to be a big problem, and you want to get rid of them if possible. So how could you go ahead and move forward and try and do that? As we said back in the beginning of the presentation, you will tend to be making calls to multiple different API services. So you're going to have a secret sitting there, or an API key at a minimum for each one of these services, most likely. So that's lots of secrets to try and protect, lots of chances to make mistakes. So typically you will use a proxy pattern and delegate a sort of master secret for your application. So that secret will still be stored on the app. It's still vulnerable. And then API calls will route using that API key into the server, which will then know the API keys of the end destination services, and will go ahead and proxy that traffic with the appropriate keys out to those services. So you've reduced your problem from n secrets down to one secret, but that secret's become pretty darn important. But it is easier to put all your resources on defending one secret than it is in defending a mix of them. Not to mention that as these keys change over time, potentially, you have a maintenance issue that's magnified. So like most good computer science problems, indirection is always something to at least think about. So is it possible for us to be able to offer a secret as a service rather than just having the secret sitting there on the app? So imagine an app wants to go ahead and make an API call to the server. It could go to a service and say, can I have the secret for this? So that's one thing to do. We really haven't changed the problem too much. There's not a secret on the app per se, but now we have a communication link to another server. So it seems on first glance we may have actually made this problem a little bit tougher. But one of the techniques that you can use is to go ahead and perform some sort of integrity measurement on your app. And so imagine the app is going to request a secret from the app authorization service. The app authorization service would like to give you that secret, but only if you're who you say you are. So typically this kind of attestation approach involves adding an SDK to the app. And when the app wants to make a call to the app auth service, it calls through the SDK. The app auth service will send a nonce back to avoid replay attacks and will challenge the app to perform a certain number of tasks to identify that it is the original app, it's not been tampered with, it hasn't been touched, it's exactly as it was when it was originally registered with the authentication service. So this is how you make reliable the check to make sure that there is a valid app there that you're talking to, and it's okay to pass the secret from the authorization service back down into the app, which will then take that secret potentially and pass that over to the API server. The one objection you might have to this is, hey, we have a communication link between the app and the app authorization service, and you told me those things are a little bit fragile. It's a lot easier to defend one very well-known link. You can do a lot of specialized thing on one link there than it being open to any possible routes back and forth. We can also use some of the techniques we use, like with HMAC, for instance. We don't have to actually send back the secret itself, but we could use that sort of HMAC-y kind of technique, or use an OAuth 2 technique and supply a time-limited JOT token back. So what you end up with in that situation is that the app service knows the static secret. The API server you're trying to get to knows the static secret, just like it would be with an OAuth user case. And you send, the app auth service will send that time-limited JOT token back to the app, who will use that in the API call. So that's a pretty reasonable, reliable system. You get a couple benefits by doing indirection with this attestation approach. Remember we said that pinning was a bit problematic? Well, when you have a second server in the loop here, when the app wants to go ahead and make a call to the app server, he will go ahead and request for the server certificate. And when he talks to the AppOS service, he'll say, I want to talk to this particular server, and the AppOS service independently will ask for that same certificate. If there's any man in the middle in that traffic, the two certificates will not compare. If they do compare, then you're very certain that we seem to be getting back the appropriate certificate. And so we can go ahead forward. We no longer have to have any whitelists. We're dynamically essentially verifying that the certificates match. Another thing you can do is also strengthen the auth2 flow with this kind of approach. Remember we had said we had this kind of shaky client secret in the auth2 flow. If you do a client attestation and prove that the client is who they say they are, then you can add that into the auth2 flow where you're exchanging the authorization code for the access token. And you can say, instead of using the client secret, use this approval token instead, which basically says that the only way I will give you an access token is if you are the original app. So if you are an attacker trying to stuff credentials through the system, you will never get an access token through this if you're just randomly sending traffic. The only way you'll get the access token is if you're using the original untouched application. So ShipFast bought into this approach, and they set up a dynamic attestation service, and they enabled the communication to be secure. They were able to remove all the secrets from the app by instead using this indirect method and the JOT tokens. So far, at least for the rest of today, ShipRaider has not been able to break past this defense. So where do we stand at this point? This is what the architectural pattern looks like. And in this case, probably the takeaway I would really like you to get from this is that most of the time we focus on protecting the user and making sure that the user authorization is successful. I'm going to posit to you that it's just as important, maybe even more important, that we know what client, what application is making the call. So if the application is a bot, you obviously don't want to let that through. So being able to authenticate the client is just as important as making sure that you can authenticate the user. Never, ever, if possible, use any kind of static secret on your device. Use token technology instead that are delivered at runtime and can be made time limited. In the case of a user authorization, there's a user in the loop, so there's a tendency to make the lifetime of tokens a half an hour, 2 hours, whatever it would be. In the case of client attestation, when you're authenticating the client, there is no human in the loop. So these tokens can be very short-lived, a few seconds if you wanted, more reasonably a couple minutes. So even if these tokens are somehow stolen, the lifetime of them is quite short. And there's no need for any kind of refresh token technology. When the token expires, you go through a fresh attestation type process. So if the application changes over time, you're continually testing its integrity to make sure it hasn't been tampered with. It's easy to do secret maintenance here because there's no secret. So in the case of the secrets, they're shared between backend servers and they're never seen on the app. In the case of client attestation, if the attestation is requested to the authorization service, it will return a runtime token. If it thinks that the application is bad, it will still return a token. It's just a token that won't have any validity. So as far as the client goes, not only does it not have a secret, but it doesn't have any idea whether it's a valid client or not. So it can't use that kind of attack vector as well. If you do want to change the secrets, it's simply changing secrets in the back rooms. You don't have to upgrade your app to do anything like that. We've used the proxy pattern here to protect one secret, and we put all our effort into protecting that one secret. And again, we get benefits in secret maintenance. We also get additional benefits in that we've decoupled the app from the API call through the proxy server. So you can think of this proxy server as being a straight through call. An API call is made on the app and it will pass through to the appropriate API service. But if you wanted to, you could distinguish between different device types. You could have an API for a mobile app. You could have an API for a television. You could have an API for a web app. And they could all run into proxy servers, which might then adapt the app calls as they go through and send them to one or more servers. So it can be more than just a proxy server. You can start adding a little bit of intelligence to make it a full-on adapter. And the API server itself can add in those behavioral approaches. So you could very early on the front end in the API server do rate limiting or do your behavioral type approaches on top of this technique. So as I said to you, I think that authenticating what is just as or more important than authenticating who. And I want to stress that ShipFast and ShipRater are entirely open source. So if you're interested in playing with these, they're available on GitHub, and there's a sequence of 4 articles at this point on Medium about using ShipFast and ShipRater and going into this in more detail. More will be coming. They're also available on the approved blog website. So we still haven't broken it yet, but ShipRater will return at some point. Okay, these are some additional references for you. The ShipFast references I've already mentioned. A sequence of 3 articles on mobile API security that are available on Hacker Noon as well as our blog. If you're interested in going in more detail in OAuth 2, I highly recommend the book by Justin Richter and Antonio Senzo. It's a really good overview and goes into OpenID Connect as well. And there's a lot there. I go back to it fairly frequently, and there are some sample implementations of OAuth 2 flows if you're interested in that. And also the technique of adapting the OAuth 2 to add attestation into the flow is available on this Hacker Noon article as well. There's some open source code with that as well. And that's it. Thank you very much. Questions, please. I put you all to sleep? Yes, sir. Oh, whoop, hang on just a sec. I promised that I would do that. Okay.
Are people doing things with that auth server service where they're going out of band to like revalidate the device that is using your OAuth token or something? So like, let's say you had the TV that you you connect to a service, you do the initial authentication. After that point, it refreshes on its own. You know, are people doing things where it's like they're forcing the user, you know, to through some out of band thing like a ping identity type of prompt on their phone or whatever, like, hey, this device is using your accessing your account still. Did you still want to do that?
Yes and no. Yes, if you were in a sensitive application, you still might want to do that. It becomes a user convenience issue. Do you want to potentially annoy a customer versus do you want to risk the customer losing lots of stuff? So it's a trade-off, but there's certainly nothing preventing you from doing that. Any other questions? I'm going to start asking questions to you.
So on the last diagram, you have sort of the secret service, I guess, on the bottom.
Yeah.
And then you have the auth on the top. You also have the API server as a third thing. Theoretically, you could have merged the 3, right? And the API server would be the one routing and doing all the other work, right?
Yes, absolutely. The OAuth 2 service I kept separate because I actually would encourage people to use third-party implementations just because it's a standardized protocol and they've been pretty well bullet tested. The AppAuth service I kept separate for illustrative purposes. There's nothing preventing you from running it on the same piece of hardware. It's so quiet.
So if I understood correctly, the client attestation works by asking the client to do some type of work.
Mm-hmm.
Would would ShipRadar be just able to reverse engineer the app and try to do the same type of work?
So yes, you do understand that correctly. And theoretically, like all crypto operations, it could, if it had enough time and enough interest, figure out how to do the same work. But it's a cryptographically valid type approach that you would use. So it would be too expensive, like a few centuries to reverse engineer something. But that's the art of how do you do that attestation in a way that is a minimum latency type activity, but covers just, if you recompile an app, you want to fail that attestation. So there's an art involved in doing that correctly.
Okay, thanks.
Over here.
So when I was watching your example, I was thinking a lot of Pokemon Go, actually, and Niantic and all the
Yes.
stuff they went through when people were reverse engineering the API and stuff like that. And how and where does like protocol obfuscation fit in here? Stuff like protobuf, and do you recommend that at all in API security?
Good question. So first I'll say that Pokemon Go was like slide 4 in this presentation.
Yeah, I'd
but
recognize it, yeah.
I cut it out because I was worried I was going to go too long. They're a poster child of how to go out with an open API, realize, figuring out where these little characters are is too expensive. Let's get rid of that feature. And all these users come back and saying, no, we want those features. We're going to reverse engineer this API. And then you're in this back and forth, which Niantic had to go through, pissing off users, adding more and more features, very similar to what's going on here in ShipRadar. It's good motivation. Obfuscating your API traffic, it really boils down to, do you trust TLS or not? The presentation here before was about TLS 1.3, so that communication layer type encryption will continue hopefully to get better and better. If you have sensitive traffic, yes, I would encrypt that traffic using, instead of HMACking the signature request, negotiate a private public key kind of type setup. There are techniques like JOT tokens that don't have to use symmetric encryption. You can use PKI. So go through and decide how much effort you want to make to obscure those API calls. Protobuf, I think, sure. gRPC, if you want to not be on REST where everybody else is at, go for it. It'll give you a little bit of buffer, but I don't think that much because it's a very structured approach and it can be reverse engineered with just an extra tool or two. So, so I would go probably for full encryption. The other bit is kind of a security by obscurity kind of play, and it'll be short-lived.
And eventually they ran into the challenges of trying to say that a device was valid. They ran into just armies of bots that were actually emulated hardware, pretty hard to detect if they were not phones or real phones.
Right. So, yeah, I didn't mention that. I probably should have stressed that a little bit more. One of the things that you want to do when you're attesting a client to see whether they're authentic is not just that kind of challenge response I was talking about, but you need to figure out, is the device rooted? Is it running in an emulator? Is it running on, say, even something like, is it running on an Intel platform? That's probably not an Android phone. Is it running in a debugger? Is Frida, which is a framework, is that installed and running? So in a practical sense, you need to check and make sure that the device is as sanitized as it can be. But again, as a vendor, you run into a problem. Okay, the guy's device is rooted. Do I let him go through or not? If I let him go through and he just is an enthusiast and he's rooted his phone, great. If I let him go through and it's a malicious attacker, I've given him a lot more power. I don't want to lose my customers, so I'm probably going to let the rooted phone get through. So it's, there's a little bit of cat and mouse that you have to go through there. Any other questions? Okay, well, I'll be around for a few minutes if anybody wants to come up thanks, and thank you very much for attending.